handle diagram, you can actually just use that nice handle diagram to assert that your manifold has some kind of geometry. And this is a theorem of Eli-Ashberg. And what it says is that if you have 4 manifold X, which admits a handle diagram that doesn't have any 3 or 4 handles, and that handle diagram has that the 2 handles satisfy a framing condition. And I'll say more about that condition in a second. Then what do you get to conclude? You get to conclude that your 4 manifold is symplectic. In fact, it's a symplectic filling of its boundary. And in fact, it's even a Stein filling. So Andras has said some things about those words in his class, but I'm not going to say very much about symplectic topology at all, except that having a handle diagram like this lets you say that indeed you are symplectic, and that is the reason we'll have the inequality we're going to have in a minute. So let me tell you what the conditions are. So to start off, you have no 3 and 4 handles, and then you want to isotope the 1 and 2 handles until your diagram looks like this. So what does like this mean? You line all your 1 handles up over here. Everything's got to go through them horizontally. Your 2 handles could be a hot mess. That's fine. Let's gather that up in some big tangle and then braid close. So first off, isotope your handle diagram like that. You can always do that. Second off, you want to make all of your, well, whatever. You want to make all of your horizontal sort of extrema, those guys, look like cusps. So isotope your diagram so that you don't see any sort of direction changes and you do see cusps. And then you also want to isotope your diagram so that all of your crossings are of this form. And what is that form in particular? I'm asking that the overstrand be the negative one. So far, all of these conditions aren't actually any requirement. Any handle diagram with only 1 and 2 handles can be made to look like this. So put your handle diagram in this form. And now the real condition, the thing you might not always be able to arrange for, is that if you look at the framing, Fi, on your ith 2 handle, and by the way, your ith 2 handle has, it's represented by a curve in your diagram, which we'll call di. Then what you need to have is that framing had better be the writhe of the curve minus the number of left cusps minus 1. I'm seeing some chat pop-ups. Anything I should address? Okay.
No, I think you're good. I think you're good.
Okay, great. Thanks, Carl. So before I state our bound, let me just try to let me give you an example of putting a handle diagram into this form. This is our X from last time. So this is the manifold we're going to try to show doesn't have a torus generating homology. Okay, what do we need to do? We need to make our 1 handle be this big guy off to the side. And now our 2 handles, the green one, it doesn't really link the blue one. And we can isotope it around so it looks maybe like this. It was in pretty good shape already. Our crossings already looked sort of right. And I won't draw it, but we're braid closing up here. And you can isotope the blue 2 handle so that looks like this. Oops, what have I done? There. Okay, and they should both be 0 framed. So hopefully I've just put our handle diagram into a form satisfying at least the top 2 conditions. And now we need to check the third one. So, all right, what's the writhe of my green curve? It looks like all of my crossings are positive. And my green curve has one left cusp. So it looks like this quantity right here, which by the way is called the Thurston-Banach number of the curve. This is 2 in this case. So my framing does not satisfy this rule. It's too big. Dear. But we can get around that. What we do is we introduce some extra unnecessary cusps. There we are. So what that does is doesn't change the manifold I'm describing. It does up my number of cusps and it drops my Thurston-Banach number here to 1. So the green handle has what we need. And the blue, again, if you check the Thurston-Banach number, these are all positive crossings. So it looks like Thurston-Banach number is 2 right now, but you can add an extra zigzag to bring it down to where we need to be. Any questions so far just about the statement of the framing condition or putting our example into that form? Okay, then what's the theorem? Well, it tells us that for one, and Andras is talking about this more in his class, but let me just assert for now that there's a cohomology class associated to your 4 manifold that is sort of a particular cohomology class coming from the symplectic structure. And for that cohomology class, the following is true. Let me finish stating the theorem and then I saw that chat question. So if you take that preferred homology class and you pair it with any second homology class, you add on the square of that second homology class, this quantity here is exactly this, is going to give us the kind of bound we want. So this is a lower bound on twice the genus of sigma minus 2 for any smoothly embedded surface sigma representing the homology class. So this would almost be sort of exactly the sort of thing we wanted if we knew how to compute the left-hand side. So you know how to compute this. This is just the intersection number of whatever homology class you're interested in. And in fact, this can be computed from the diagram as well. So this quantity can be read off by just taking, so you know that your 2 handles generate your H2. So for the homology class that you're interested in, you want to write down a linear combination of, I'm writing too close to the bottom of the screen. You want to write down a linear combination of 2 handles, which represent that class. And for that linear combination, this quantity is going to be the sum with the same coefficients of 1/2 the difference between the number of up cusps and the number of down cusps. Okay, and an up cusp means probably what you would guess it means. If we orient our handles and we walk along them, when you go around the cusp, if you point up, that's an up cusp. And I want to comment that the orientation of the 2 handles matters here. It matters in what this quantity comes out to be, but it's also fixed because I'm demanding that you take a linear combination of your handles that gives the homology class in question. So that is going to be sort of a well-defined oriented set of the 2 handles. How are we doing, Kyle? Anything for me?
So far, so good, I think.
Great. So let's try to apply this junction inequality in practice. Here it is stated again. Here's our x again over here. So we're going to finish up the proof from last time. We're going to try to show there's no torus in here generating homology. And we can just write this down from looking at the diagram, right? So first off, an exercise is to check that the generator of H2 in this 4 manifold is going to be given by one copy of the green 2 handle oriented as I just did, and one copy of the blue 2 handle oriented as I just did. And so now we need to count our cusps. So this looks like up, up, and down and up, and here, up, up, up. Where am I going? That should probably be down. Great. Okay. So now we're ready to just read this off. We need 1/2 of 2 plus 2. So that term right there is this. This quantity was 2 for each of my handles. Self-intersection number is 0. You'll have to remember that from last time, but these were 0 traces. And now that's a lower bound on twice the genus of any surface representing this, -2. And so I think hopefully that implies that there aren't any tori here. Questions? So what we've just done is we've shown that there are 4 manifolds, homotopy equivalent to S2, that are homeomorphic and not diffeomorphic. We distinguish them by distinguishing their genus functions. And we used to, we use that effectively, but we found a pretty small gap in the genus functions. One of them has genus 1 and the other has genus at least 2. So maybe a reasonable exercise is to show that there does exist a genus 2 surface embedded in X generating homology. And a much harder exercise, but I think this is a good challenge for anybody who's maybe really trying to wrap your head around and get good at using these techniques in practice, is to try to show that there exist exotic knot traces, maybe one with a torus generating homology and one with where the minimal genus surface you need is arbitrarily large. And that latter exercise is reasonably difficult. When I tried to do this for myself, I didn't manage it. But when both of your TAs independently in conversation with me tried to do this for themselves, they did manage it. So I don't know how hard that makes you think this exercise is, but I claim it's not true. So that finishes the proof that there are exotic homotopy S2s. I wanted to make a couple of remarks about it before I move on to a corollary. So the first remark is we use this adjunction inequality for Stein 4 manifolds. And the reason this is the adjunction inequality that I gave you for this lecture series, and the reason it's my very favorite one, is that it's incredibly easy to use, right? Like we just drew a diagram that satisfied some nice properties, and then we counted some stuff in the diagram, and we got a bound on the minimal genus of a smooth surface representing homology class. And if you've ever had to do that before in another context in your life, you might have had to count pseudo-holomorphic curves or something like that and not count up cusps. So this is a great adjunction inequality for usability. When you can use it, the remark though is that not all 4 manifolds are symplectic or Stein, and not even all 4 manifolds without 3 or 4 handles admit a Stein structure. Okay, so you can't always use this tool, but if you're just trying to, build Exotica, then you're the one building it. Build something that is Stein, where you can use this tool. At least I like to try that first. And maybe the second remark, something I told you should have in mind as we prove all the theorems we're going to prove in this mini course, is that that's nice theorem. Could I use this to answer that question in closed form manifolds? And so the first answer here is that, like, how did we distinguish these guys? We use the genus function, and that should work just fine for closed manifolds that have some B2. So genus function as an obstruction works for closed. But when you use a genus function, you have to have some lower bound somewhere. We got ours from the Steiner junction inequality. That really came from having this symplectic structure on our manifold. And what's not going to be so easy in closed is finding symplectic or really nice geometric structures on really simple closed form manifolds. So maybe let me just write that finding simple closed symplectic is hard. There is some kind of a junction inequality for closed symplectic manifolds, not quite this. And if you want to know more about why this is so hard, you should go to Samira's talk later today. So I'm going to give a corollary of this theorem, of the fact that there are exotic homotopy S2s. But before I do that, let me ask for questions or clarification. Okay. So to set up the corollary, really to motivate why you should care about it, let me state a lemma. And I'm going to prove this lemma in my 5th talk. But if the lemma sort of burns a hole in your pocket and you need to know how it goes before that, you can ask Kai Nakamura. Let me state the lemma. What it says is that if you have a pair of knots with homeomorphic zero surgeries. So remember, the zero surgery is the same thing as the boundary of the zero trace. Now we have a pair of knots with homeomorphic zero traces, so we certainly have this. So if you have knots like this, such that K is the boundary of a disk embedded smoothly into B4. So I suspect many of you know that there's a word for this. We call knots like this slice, and Allison used this word yesterday. I just wanted to make sure that it got defined. Okay, so if K is slice and J is not slice, then that's kind of good news. That implies that the Poincare conjecture is false. Okay, so proof of this later, it's not immediate. The corollary I want to discuss is going to get at whether it's reasonable to expect this lemma to happen, whether this is maybe a remotely reasonable approach. To state the corollary, let me first generalize this notion of sliceness. So many of you will know this, but let's make sure that we know that we say that knots are concordant if they co-bound an annulus, and that annulus lives in S3 times I. So the picture you should have in mind here, so concordance it's an equivalence relation. So we're comparing, a knot K0 and a knot K1. They both live in S3. To compare them, we'll think about the sort of boring four manifold S3 times I. And then we'll say that they're concordant if they co-bound an annulus. And maybe a comment, it's, S3 times I doesn't have any H1. So K0 and K1 certainly co-bound some surface in there in the trivial homology class, and concordance is really demanding that it be an annulus. So the concordance, by the way, in particular, is an example of this sort of what's the smallest genus surface you can find in a homology class with given like boundary requirements sort of question. And an exercise, if you're new to thinking about concordance, is that you should check that this concordance thing is just a nice generalization of sliceness, in that a knot is slice if and only if it's concordant to the unknot. Okay, so I made that definition because I wanted to be able to tell you that there was a conjecture that said quite strongly that the conditions of this lemma should not happen. This is a conjecture of Octolute and Kirby. It was on the original Kirby problem list. So what they conjectured is that if you have a pair of knots with homeomorphic zero surgeries, then they just have to be concordant. And so in particular, this doesn't happen. But the corollary of the theorem that we just proved is that this conjecture is false. Knots with the same zero surgery do not have to be concordant. And it's open whether, I suppose you can deduce this, it's open whether it's possible that one B-slice and one not. So I want to sketch the proof of the conjecture. Sorry, the proof of the corollary. Any questions before I do? Okay, so we're gonna let K be our knot from our proof of exotic knot traces, the one that has a T2 generating homology. So let me sort of schematically draw that torus as, I don't know, looking maybe something like this. So as Allison did yesterday, I've drawn a kind of convoluted picture in my schematic to remind you that I know this torus generates homology, but it might run over the handle a whole bunch of times. It is, however, not too hard to show using some general position nonsense that where that torus intersects the two handle doesn't have to, it can be taken to be not very interesting. It can be taken just to be copies of the chord disk. So we can focus our attention just on the part of our torus that lives in the four-ball part of our trace, which maybe looks something like this. So this is genus 1. And in our schematic, it appears to have 3 boundary components. In general, I guess it just has some odd number. So, okay, fine. We get this kind of interesting surface embedded in the four-ball. It's got boundary 3 parallel copies of our knot K. And an exercise is that those are 0 framed parallels. And so now what I want to do is I want to suppose for a contradiction that our other knot J from the proof of the theorem was actually concordant to K.
Lisa,
So yeah.
can you just say one more time your transition from the picture on the left to the picture on the right?
Yeah, all I'm doing is I'm focusing on the four-ball. So with some general position nonsense, you can decide that the part of the torus that runs over the 2 handle is just parallel copies of the core disk. So there's kind of nothing interesting going on here. So this is just the interesting stuff. Genus 1, 3 boundary components. More questions? Okay, so we're assuming that our knot J is actually concordant to our knot K. And what we're going to do with that is we're first going to enlarge our four-ball. Oh, I drew it quite enlarged, but that's fine. So we're just going to stick an S3 times I collar onto the outside of our four-ball. This is still a four-ball. And since we're assuming that K is concordant to J, what that means is that I can find some annulus running from K out to the knot J in this outer boundary. And in fact, I can take parallel copies of that annulus and get 3 annuli here, running out to 3 copies of J. Let me finish this. Okay, so now I have a bigger four-ball. it's got this sort of inner interesting genus 1 surface 3 boundary components. Then we stuck an annulus onto each boundary component. So it's still genus 1, 3 boundary components, but now my boundary components live on parallel copies of J. And then what we can do is we can stick a 2 handle to this enormous 4 ball along J. And what's this manifold? This is the 0 trace on J. And what do we see sitting inside of it? Well, I can take copies of the core disk up here and use them to cap off all of my boundary components of all this stuff we had in the 4 ball. So what did we get? We got this genus 1 surface in the 0 trace on J. And it runs the same number of times over the 2 handle as this surface did over here. So that's going to be algebraically once. So it generates H2, and that's a problem. Questions?
So you proved that like the shake genus has to be the same, but then you proved that the shake genus in fact was not the same earlier using
Yeah,
what again?
I'm really showing indeed that if they're concordant, then they have the same shake genus. But what we really showed in the proof was that they don't have the same shake genus.
Sorry, what was that technique again? Just to kind of wrap it all in a.
Sure. So maybe if there's a lemma hiding under the proof of this corollary, it's that concordant knots have the same shake genus. And shake genus is defined to be minimal genus surface in the trace generating H2, and we've already showed that R knots don't have the same shake genus. More questions? Okay, so I sort of promised you 4 theorems on the first day: exotic homotopy S2s, exotic contractible, exotic disks, and that there's more to life than exotica. And there's also 4 manifolds that are simply connected that need 1 handles. So the plan for the rest of today is to do exotic contractible, and we'll do 1 theorem each for the remaining talks. So let's do exotic contractible. So this theorem was originally proved by Akalut and Ruberman in 2014. First statement, there exist X4 exotic contractible. Exotic meaning there's some other 4 manifold homeomorphic, but not diffeomorphic to it. That other thing is smooth. And then a strengthening of the theorem / simplification is that such that X can be described with a single 0, 1, and 2 handle. So not only are there exotic contractible manifolds, but they can be written down they have really simple handle diagrams. And in fact, we're going to show like not only does X have such a simple handle diagram, but its exotic friend will also. So how's the proof of this going to go? It's pretty straightforward. Logically, we're going to build X and X prime contractible that have the same boundary. Then we're going to show that they're homeomorphic. And then we're going to show that they're not diffeomorphic. Let me jump into the first part. What are these guys? So I've drawn one of them for us here. It's going to be this 4 manifold X. For the rest of all time, I probably won't draw my entire handle diagrams. I will let you braid close in your imagination. So if I draw something like this, we're just looping around there and I'm saving space on the slide. So this is X. The first thing we need to check about it is that it's indeed contractible. So let's think about as pi1. We have this one handle. So that's going to give us one generator of pi1. It'll be a curve that runs over the one handle, so something like this. And now we have one relator. You've already seen this, and you could just argue, like by looking at it, that you can homotope this relator, maybe by changing this crossing here, so that this is, homotopic to a curve that just runs geometrically one time over the handle. So you have no pi1. But I want to point out that if you were like not feeling like actually looking at the picture, you could argue just because there's only one generator of our group, that the fact that I know that this relator links once with the one handle is enough to let me know that indeed this relator has to exactly kill the generator. That'll be a useful observation in a second. Okay, so we have no pi1, and I'm going to let you check that we also don't have any homology. Very good. So now we need something else, hopefully contractible, with the same boundary. We only know one trick for writing down 4 manifolds that have the same boundary, so we're going to try to use it. That trick is the same thing we used last time. It's this little sleight of hand where the boundary can't tell whether you attached a 1 handle with dotted circle notation or attached a 2 handle with 0 framing. So we'd sort of like to maybe act like this 2 handle was actually a 1 handle, but we can only do that if this 2 handle is an unknown. So we have to check that. So now I will actually close my braid. So what's going on here is I'd like to write down another 4, I'd like to not erase my picture. I'd like to write down another 4 manifold with the same boundary as this one. I'd really like to dot this blue curve to do it, but I need that blue curve to be an unknown. So we're just checking that here. We can just start simplifying this, and that'll indeed be the case. So there's like some R1s right here. Get rid of all of that. There's some more R1s up here. And maybe I'll let you finish this up at home, but this is looking simpler. This is indeed an unknown. So I'm actually allowed to do this thing right here notationally, put a dot on that. So I want to think of this blue curve as a 1 handle. And well, certainly we can think of that red thing as a 2 handle. This is going to be our manifold X prime. So very good. That's an X prime. It's got the same boundary as my contractible guy. I also need it to be itself contractible. Again, we just have one handle. So there's one generator of pi1. And by the same argument we sort of just mentioned, that if you have just one generator in your group, then if you can sort of see that that your group abelianizes to nothing, then in fact your group was nothing. So sort of normally, if I had more 1 handles here and I wanted to write down pi1 of this, I would really need to see my generator. So I'd really need to isotope this picture around so that the blue looked like a boring unknown and write down my relators from that picture. And I just don't want to do that live. So that's why I said the thing about 1 generator. Careful though, in the rest of your life, when you have more than one handle, you can get into trouble if you don't actually straighten things out. Okay, and then you get to check that the homology of X prime is nothing. And that's the constructive part. We've built a pair of contractible manifolds that have the same boundary. Let me pause for questions. So we have to show now that these guys are homeomorphic. And when we were doing exotic homotopy S2s, to show they were homeomorphic, we found some contractible manifold inside them and showed they were related by swapping it out. And we used this theorem of Friedman to tell us that swapping out a contractible manifold for a different contractible manifold doesn't change your homeomorphism type. Here, we don't have to work that hard at all. We just appealed directly to the theorem of Friedman, which tells us that for any two contractible manifolds with the same boundary, there is a homeomorphism. So they're homeomorphic just like completely for free. Great. So the real work that remains is to show that they're not diffeomorphic. To tell you how we're going to do that, let me start off by telling you a theorem, an observation that's going to seem a little pedantic, but let me point this out. So the observation is that if there was a diffeomorphism delta from X to X prime, then if I look at delta restricted to the boundary, that's some boundary homeomorphism. And what do we observe about that boundary homeomorphism? It extends smoothly. Okay, so that sentence is a bit circular, but the reason I'm saying it is because this is actually what we're going to obstruct. We're going to show that there are no boundary homeomorphisms from X to X prime that extend smoothly. So there'll be two steps to showing that. Before I tell you what they are, let's just give a name to the sort of boundary homeomorphism that God gave us, which is the one that just observes that these surgery diagrams of the boundary are bang on the same. So we'll call that phi. So the first thing we're going to prove is that phi does not extend smoothly. And the second thing we're going to prove is that all homeomorphisms from the boundary of X to the boundary of X prime are isotopic to phi. I know I paused for questions recently, but let me do it again to make sure we're clear on how this argument's going to go before I start actually doing A. Okay, great. So to show phi doesn't extend, we're going to first make the observation that if it did, we could use that to build a diffeomorphism between some different manifolds. And what we would get is that if you took X and you glued to it a two handle along any curve gamma you happen to like in the boundary using any framing, that bigger manifold, X with a two handle attached, that would be diffeomorphic to the manifold you get by taking X prime and gluing a two handle to it along the image of your attaching data from the last time. So let me draw that in the schematic over here. So you choose any gamma you like in the boundary of X, and you attach a two handle to X. There. So now we're supposing that I had a diffeomorphism from X to X prime. And we're considering X prime with a two handle stuck to it along phi of gamma. And well, you can write down a diffeomorphism between these bigger manifolds, which is just going to be this phi between X and X prime, and something that looks like the identity up here on the handle. And because we adjusted our gluing information here, this will be a continuous diffeomorphism between these spaces. So, I mean, that's fine. It's true, but you should ask yourself or me why we're doing this. Like, I'm trying to show that X is not diffeomorphic to X prime. And what I've pointed out is that if they were, then some bigger manifolds would also be diffeomorphic. But I have a very good reason for wanting not to worry about X and X prime and instead worrying about bigger manifolds. And the reason is because I don't have any tools in my arsenal for showing that X and X prime aren't diffeomorphic directly. And I'll say a little bit more about that in a minute. The thing we do know how to distinguish is for manifolds that have some H2. We know we can tell them apart by considering their genus function. And so we couldn't apply that to contractible manifolds, but we can totally apply that to contractible manifolds with a two handle stuck to them, which are homotopy S2s, back into familiar territory. So this is exactly what we're going to do. And the gamma you want to consider, I mean, you can do whatever you want, I suppose, but a gamma that I think is nice to consider is this one with the zero framing. And, you know, what's our boundary homeomorphism? It's just the one that identifies these surgery diagrams by not moving anything. So this is the image of gamma. And what I'm going to leave for you as an exercise in checking that you understood the statement of the Steiner junction inequality from the first proof is to show that X union a two handle along 0 is not diffeomorphic to X prime union a two handle along the image of gamma. And this argument should go exactly like it did in the last proof. Any questions? Cool. So,
Sorry, quick question, just to clarify. So you're also like implicitly assuming that phi actually sends like your yellow trefoil to the other, like this actually is the right map.
no, I am not assuming that. I know a boundary homeomorphism phi. It's the one that says don't move anything in the diagram.
Right, okay.
And so that homeomorphism definitely does send yellow to yellow.
Right. Okay, thanks.
Yeah. But indeed, I don't know anything about any other boundary homeomorphism extending or not at present. Okay, so it should seem like we are an epsilon of the way towards proving these manifolds aren't diffeomorphic. Like we showed that one boundary map isn't the restriction of the diffeomorphism. Now, what about all the others? And okay, I guess what I already blew my punchline by telling you line B that there aren't going to be any others. And the reason why that's not so shocking is first, let me remind you that generically, three manifolds are hyperbolic. And the self-homeomorphisms of hyperbolic manifolds are really well understood. It's the theorem of Moscow and Prasad that for Y hyperbolic, all homeomorphisms from the manifold to itself are isotopic to isometries. And it gets better, there's only finitely many isometries. And it gets better, generically, there should only be one. So when you sort of set out to build Exotica with boundary, if you use this kind of dot zero trickery, which is very common, you get a boundary homeomorphism. And in fact, generally speaking, it's going to be enough just to show that that one doesn't extend, because probably there won't be any others. So to finish the proof, we just have to check that we are indeed in the generic setting. And And this is something you can check using a computer program called Snappy. So I'm not going to talk about Snappy right now, but one of your TAs volunteered to tell you how to use Snappy in practice in the sessions, and maybe I'll volunteer the other one and therefore not tell you which one it was. Anyway, you can ask your TAs how to use Snappy in practice if you actually want to use this in your life. But let me just tell you, things Snappy can check for you is that indeed the boundary of our X is hyperbolic, and indeed the boundary of our X has a unique isometry. Questions?
Is there some way to know whether the boundary is going to be hyperbolic while you're constructing it, or is it just like you make something and then put it into Snappy and then check whether or not it is hyperbolic?
I'm afraid a bit more the latter. I mean, one thing you should do is try not to have essential tori. Like sometimes if you use some kind of satelliting operation or something in the way you wrote these things down, then you might spot that you can't be hyperbolic for that reason. So the only sort of real art here is violate any tori that happen to show up in your picture.
Okay, thanks.
I got a question. What's the fundamental group of this three manifold? Don't know. Did Snappy can tell you that, but I didn't look. Is there a reason for the question? Okay, so a couple of remarks before moving on to a corollary of this theorem. I guess one challenge I wrote here, this is sort of silly, but these are the simplest exotic contractible manifolds I know about, and I'm just sort of amused by these things. So if you can come up with what simpler might reasonably mean, and then find any simpler ones, that I'd be interested to hear about them. But maybe some more substantial remarks are, generically the boundary of these manifolds will be hyperbolic. You'll only have the one isometry, the one homeomorphism to worry about. But if it's not hyperbolic, it's okay. You still have options. And the reason for that is because we understand three manifolds pretty well. So even if you have, say, a non-trivial JSJ decomposition, you actually probably still know a lot about the self-homeomorphisms of that three manifold. And sometimes you can prove things like, maybe even if there's arbitrary, like if there's infinitely many homeomorphisms from here to here, maybe you can show something really strong, like, yeah, but all of them send this yellow curve to this yellow curve. And then you'd still be able to just obstruct all of them from extending, things like that. Oh dear, we're stuck on this page. Okay, and then the second remark is we're supposed to pay attention all the time to how reliant were we just on the boundary. And the answer is very, very reliant. So for one, in part A of part 3, you use a Steiner junction inequality again. So like we were using, the boundary is sort of subtly coming into the fact that we built a simple thing that has a symplectic structure, but then it's coming in again in a much bigger way. We really had to inspect this boundary three manifold. We had to classify its homeomorphisms or some non-trivial three manifold topology there. And I just completely don't know how to get away from doing that. So maybe a much better challenge problem is to reprove this theorem with like an intrinsic, I don't know, give another proof of this theorem with less reliance on boundary maps. Okay, so don't use this argument where you try to show all the boundary maps don't extend. Use something else. Use an obstruction that's actually intrinsic to the contractible manifold. That would probably be very helpful towards applying these tools in the closed setting. And we don't have anything like that, to my knowledge. So I want to wrap up with a corollary of the existence of exotic contractible manifolds with a single 1 and 2 handle. And some context for the corollary before we give it. There's an incredible theorem of Dave Goodbyes from the early 80s that says that there exists only one not K in S3 with an S1 times S2 surgery. So not all 3 manifolds have an S1 times S2 surgery, but S3 does. And what Dave proved is that it's unique. And that might cause you to wonder, and indeed sort of in some places where property R was written down, a sort of follow-up question was also written down, which is, do all 3 manifolds which have an S1 times S2 surgery have only the one? And the corollary here is that the answer is no. So our boundary X admit multiple, and in particular 2 that we know about, S1 times S2 surgeries. Reference comment, the existence of 3 manifolds that admit multiple S1 times S2 surgeries was also proven independently and without reference to exotic contractible 4 manifolds at all by Kim and Park in 2018. I'll sketch this. Let me check for questions before I do. Okay. So the first thing we want to observe is that there exist knots J and J prime in S1 times S2 with a boundary X surgery. So what are those knots? We look at this surgery diagram of boundary X, and we can sort of think of it as, first do surgery on the red curve. So that gets you to the boundary of a 1 handle, that's S1 times S2. And then there's a curve in there, it's the blue one that surgeries you out to boundary X. So J is maybe this blue curve here. And similarly over here, in the boundary of the 1 handle, which is S1 times S2, you can do surgery on the red curve to get yourself out to boundary X. You can also check, and I'm not going to write out all the details of this, that the fact that X is not the same 4 manifold as X prime implies that J is not isotopic to J prime. So what you should think here is, if these were the same 2 knots in the boundary of a 1 handle, then attaching a 2 handle to them would give me the same 4 manifold, and these are not the same 4 manifolds. There's a little work to do about the framing. Okay, so this is not what we wanted to prove. This is what we've shown so far, is that there are 2 knots in S1 times S2 that aren't the same, that surgery me to boundary X. So now we sort of just need to find like dual knots going the other way. And that's not so hard to do. So what we're going to do is we're going to consider K to be the core of the surgery solid torus for J. So let me say what I mean by that. We start in S1 times S2, the boundary of our 1 handle. And to get to boundary of X, we cut out neighborhood of J and glue it back in a funny way. And I can pin down a knot in boundary of X by saying, well, you know, that surgery solid torus, it's got a core. And when I glue it in a weird way, that core is still a knot in my surgery manifold. That's the K I'm interested in. And similarly, K prime for J prime. And then what you want to check is that K is isotopic to K prime, if and only if J is isotopic to J prime. And finally, you want to observe that K and K prime both have S1 times S2 surgeries, because, you know, what is K? It's the core of the surgery solid torus that you sort of stuck in some funny way along J here. So you can just, you know, cutting out the neighborhood of the core is just cutting that surgery solid torus right back out, and you can put it back in like in the normal way, and that'll get you back to S1 times S2. Okay. And if you've never seen this business about dual surgery knots before, a nice exercise perhaps is to locate K and K prime in these surgery diagrams of boundary X. So what Dave's theorem tells us is that there are three manifolds, in particular S3, which have an S1 times S2 surgery and it's unique. And what we're seeing here is that there are three manifolds which have an S1 times S2 surgery and it's not. So a question coming out of this is which, and I think this is very not well understood. So which Y3, which have an S1 times S2 surgery, have a unique one? Are there any with infinitely many, etc.? And maybe one more final question, which isn't about this corollary at all, and is just about the statement that there are exotic contractible four manifolds, is that, you know, what we just proved is that they exist, and the conjecture perhaps is that they're completely ubiquitous. So all contractible X4 are exotic. And I wanted to stop there. Thanks.
Let's thank Lisa. Are there any questions for her?
So this last conjecture contains the Poincare conjecture, I guess.
Yes, I guess it does.
You should give it as a homework, maybe.
Okay. It's an exercise for András's class. Prove the conjecture. And take it up with his TAs if you can't. Yeah,
Other
my TAs
questions?
are revolting in the chat. Oh, sorry, go ahead.
Oh, other questions for Lisa?
So this conjecture is would imply that the Poincare conjecture is not true, right?
Yeah, that's right.
Okay.
All right, if there are no more questions for Lisa, let's thank her again. So we will have a short screen break to grab food or just get away from the screen, and then we will come back. I think, hold on, I'm sharing a screen right now. Okay. So we'll come back at 12:40 to have lunch together, and the topic for the day in the breakout rooms will be lightning talk discussions. So there will be a breakout room for each lightning talk speaker. So see y'all in 20 minutes.